All right, Calc 1 students, in Chapter 3, Section 4, we're talking about the chain rule. And what the chain rule is going to allow us to do is take the derivative of composite functions like f of g of x. Let's see what that looks like. I can get my screen to scroll here. Yep. So here's an example of a composite function. In f of x, we have an outer function, which is the square root function, and there's a second function that's happening inside the square root, which is x squared plus 1. So the chain rule is going to allow us to take the derivative of functions that look like this. And as I've been doing in the past few videos, I'm just kind of scrolling through these slowly so that you can give these a read if you want to, or pause and read this articulation of what the chain rule is and how it works and how the different functions relate to each other. There are some different notations. This is Leibniz notation, the dy over dx. Here are the two notations side by side. The top one is using prime notation to indicate that we've taken the derivative. So capital F being the original function, you can see here capital F is f of g of x, or noted this way, f of g of x. And when we take the derivative of it, we get capital F prime of x. And then we're seeing some unusual stuff. I see my outer function f has a derivative, and then inside there the g of x is still regular g of x. Only the outer function has had its derivative taken, so to speak. And then afterward, we're multiplying by the derivative of the inner function. That is correct. Leibniz notation tells us the same thing. We've got dy du. It's with respect to u because in Leibniz notation, u is the inner function. And then afterward, we are still multiplying by the derivative of the inner function u with respect to x. And you'll notice that, how do I put that back? How did that even happen? Let's go this way. Sorry about that. Where were we? The inner function. Now I have to select my pen again. All right, there we are. The inner function u is with respect to x, which is why right here we have du dx. When I learned this stuff, I used the prime notation. That's how it was taught to me. The Leibniz notation, you may encounter it. Certainly dy over dx is a very prevalent notation. I just don't see it as often when I'm working with the chain rule. So there are those two notations again. And of course, you're welcome to read all of these things. So many things. All right, now here we are going through the process of taking the derivative of the square root of x squared plus 1. And we're being told here that our outer function f is actually f of u. So we're taking the square root of something. And if we take the derivative of that f function, lowercase f, then we take the exponents of 1/2 because it's a square root function. They're assuming that we know already that we could write f of u as u to the 1/2. So we take the derivative of that, we multiply the 1/2 out front, there it is. We keep the u value the same, there it is. We decrease the exponent by 1, 1/2 minus 1 is equal to negative 1/2, there it is. And then if we convert that back over into radical form, we have 1 over 2 times the square root of u. Now this g function, which is the inner function in our particular problem, the derivative of that function is 2x. And then there's this sort of recompiling of those components So the derivative of our main function is equal to the derivative of our outer function, which we said was 1 over 2 times the square root of u, the inner function. And here it is, 1 over 2 times the square root of the inner function, g of x squared plus 1. And then we have to multiply, don't forget, by the derivative of the inner function, which we said was 2x. The 2's cancel from the numerator and denominator. The x does not, so that has to stay up in the numerator, making this our final answer. So perhaps that is your first tour through the chain rule. Here's the other notation. There's that same derivative of the outer function, but with respect to u. There's the derivative of the inner function with respect to x. And then we go from here to here by replacing this u value under the square root with what u equals, which is x squared plus 1. Clean it up a little bit, and you got your final answer again. So either of those two notations, as always, whatever rings most true to you, whatever you think is going to be easiest to memorize, whatever is visually most appealing to you, whatever is going to help you get through these, that's the notation that you want to use, but do be aware of both of them. Well, I didn't really pause for very long on these, just in case you wanted to read this. There you go. 3, 2, slide that up a little bit. Most of this we've seen. Yeah, we saw that already. Okay. And then here we're changing gears a little bit. Here y is equal to the sine of u. Now I don't know if we're taking the sine of u. I don't know what u is. Maybe u is an x. Maybe u is x squared plus 1. Maybe u is the square root of x squared plus 1. We don't know. All we know, because we're being told, is that u is a differentiable function of x. And if that's the case, then we can still use either notation. Here Leibniz notation is being used. We're taking the derivative of the outer function, and the derivative of the sine function, we talked about it last section, is cosine. There it is. And then we have to multiply by the derivative of the inner function. There's that multiplication by the derivative of the inner function. There's the inner function u, and we don't know what the inner function is yet. So for the moment, that's just sitting there waiting for someone to tell us what u is. Once we know what it is, we'll take the derivative, drop it in. And then here is a generalized conversation about a scenario, a set of circumstances that is very common to run into, and that's where we're taking an expression and raising it to a power. In the last section's video, I mentioned we had a denominator of like t minus 2, and it was all being raised to the second power. And I said, really, we should be applying the chain rule to this, but it's okay because when you multiply by the derivative of that inner function, it's going to turn out to be a 1. So it's not really going to hurt you that you don't know to incorporate that yet. But here is the specific articulation of what it was that I was talking about back there. And it says here that if we take an expression u and we raise it to the nth power, so there's u to the n, and we take the derivative of that, taking the derivative of u to the n, then we have to take the exponent n and multiply it out front of the u, and we have to decrease that exponent by 1. The u stays the same, but then the chain rule says you have to multiply by the derivative of the inner function. So there it is. We're taking the derivative of u with respect to x. And then all of these components match up to the next line below it. And I like that notation better. So we're taking the derivative of a function g of x that's being raised to the nth power. The n multiplies out front. We decrease the exponent by 1. We multiply by the derivative of, clearly, this is the inner function, g prime of x. Maybe for me it's just because it's larger. Look, I mean, I can see the g of x, and here I can see the g prime of x. I know it's the inner function. Here, this u is just so small. I don't know. And then putting it in this notation with the du up there, that doesn't scream, don't forget to take the derivative of this. I need it loud and in my face, or I'm going to forget. Okay, so that's another more formal, maybe, articulation of the chain rule. And then let's just breeze through a couple of these, and then I'm going to switch over and look at a couple of homework problems. So here we're being asked to differentiate or take the derivative of this equation that's being raised to the 100th power. Don't worry, we're not going to multiply this out. And so here, yeah, okay, this is like a mix of the Leibniz notation, I suppose. There's no primes, but we're taking the derivative here of our original function, and you have to take that exponent and multiply it out front. There's the 100, and then keep this inner function the same. Look, there it is. And then take that exponent of 100 and decrease it by 1. There you go, it's a 99 now. And then don't forget to multiply by the derivative of the inner function. So there's that inner function again, but we're taking the derivative of it. Okay, on the next line, we're not going to multiply by the 100. We're not going to distribute it. We're not actually going to raise anything to the 99th power. All we're doing is taking the 3 and multiplying it by the 100 in order to get 300. And we're taking this x squared, and we're just moving it sort of in here into the mix. So it's 300 times our variable to its power times the expression, x to the third minus 1, to its power. And that's about as tidy as we can make it. So the chain rule is all about remembering to multiply by the derivative of the inner function. And this is definitely kind of a special case. Here we're taking an exponential expression like b to the x, and we are taking the derivative of it. So what the chain rule tells us is that if we're taking the derivative of b to the x, then that is equivalent to taking the derivative of e to the natural log of b times x. Which is true. You wouldn't normally think to write it that way, but it's true. And then from there, we can use the chain rule, because e is being raised to this power that is a combination of functions, and it ends up boiling down to this. This is what you want to make sure goes into your notes. The derivative of a constant value being raised to the power of x is equal to that same constant value being raised to that same power of x multiplied by the natural log of b. This is, or should look a little bit familiar, because we have taken the derivative with respect to x of e to the x. And you were told that that was equal to e to the x. But this statement that we're seeing right here in blue, doesn't that say that I should have to multiply also by the natural log of e? And you're absolutely right, times the natural log of e. What is the natural log of e? Don't forget that the natural log of e is actually asking us e to what power equals e? And the answer to that question is 1. So the natural log of e is actually equal to 1, which you knew at some point, you might have forgotten. That's the reason why we don't write it. When we're first learning this, we're not told that behind the scenes, the chain rule is in effect, but resulting in a multiple of 1, which we're going to exclude. that would just confuse you at that stage in the game. But here, it's coming in a little late, but it is happening behind the scenes. That's only when you've got a base of e where it turns into 1. Otherwise, you do need to multiply by the natural log of b as part of the chain rule. And then there's some conversation about the chain rule. You're welcome to check that out. Just saying that it becomes clear that it should be called the chain rule once you've got multiple nesting, or the nesting of multiple functions. It becomes clear that it's this chain of taking the derivative over and over again. And we're not going to be proving the chain rule in this video, so let's jump over and have a look at homework. A quick dip behind the scenes here, and we are in 3.4 homework. At least I think we are. There we go. Oh, interesting. Something wonky happened when I printed this to PDF, so I'm going to pause and I will be right back with a cleaner version of these homework problems. All right, that's better. Number 1 is asking us to write the composite form, or the composite function in the form f of g of x, identifying the inner function as g of x and the outer function as f of u. So this will be interesting. So our inner function, g of x, is this stuff right here. It's the radicand, the stuff under the root symbol. So we're going to write that as, if my pen will work, always a challenge getting this pen to work. G of x, I don't know if we have to write g of x equals here. I think maybe we can just write 1 plus 5x, comma, and then the outer function is the cube root function, but how am I look at this. We're being told to write it in terms of u, and so I'm going to write the cube root of u. And then eventually the u is going to get replaced with a g of x, which is going to get replaced with a 1 plus 5x. But for the moment, this is the format that we're going to use. And now they want us to find the derivative, dy dx. Let's do that. Let's make a little more room here. There we go. I'm going to take my original function or equation and write it as 1 plus 5x to the 1/3 power. And then y prime, or dy dx, equals, and let's talk through the motions. Here's the process. Take the exponent, multiply it out front, just like we always do when we're, well, not always, but when you're working with a polynomial. You would take the exponent, multiply it out front. We keep the function that was under the exponent, the 1 plus 5x, decrease the exponent by 1. I'm just going to go right at it and write negative 2/3. If you need to write positive 1/3 minus 1, and finish writing it out and then go to the next line and then do that subtraction, do that. Some of us need to literally see what happens one step at a time. So do whatever's best for you. And then here's the chain rule part. Now we're going to multiply by the derivative of the inner function. And I'm going to do that right away. I'm going to multiply by 5. However you want to do it. Instead of writing times 5, you could have written times the derivative with respect to x of 1 plus 5x. And on the next line, turn that into a 5. I'm not going to do it this way. I'm going to do it the way I had done it just a moment ago. I'm going to leave it as times 5. And then maybe I'll put a little bracket under here and say d over dx. I took the derivative of this stuff to get the 5. And then on the next line, let's clean it up. It's a fraction. And what's going in the numerator? Almost nothing, just the 5. 5's going up top. That multiple of 3 from the 1/3 is going in the denominator. And then the other thing that goes in the denominator is 1 plus 5x. Because it's to the negative 2/3 power, it needs to go into the denominator. We could leave it as 1 plus 5x to the positive 2/3 power. Or you could write it as the cube root of 1 plus 5x squared. I like it like this. We've done the chain rule again. Nice job. We do enough of these, you're gonna get the rhythm of these, and then you're gonna be bored, which is what I want. I want you to know these so well that they're boring. You're just like, it just takes time. It's not challenging anymore. It just takes time. Perfect. That's where you want to be. That's the goal. Let's take the derivative of this thing. I'm going to take the exponent of 7. I'm going to multiply it out front of my inner function. So there's the 7. I'm going to keep the inner function. X to the 4 plus 9x squared minus 2, close. Then I'm going to decrease that original exponent by 1 and make it a 6. And then I'm going to multiply by the derivative of my inner function. Chain rule. If there's an inner function and an outer function, you're using the chain rule. That is 4 x to the 3rd plus 18x minus 0. So just close it up. And if you want, if it's helpful in your notes to have this, put it in there, d over dx. We took the derivative of the inner function to get that last multiple. I don't expect that anyone would ask you to multiply this out. If they do, kick them in the shins and run, because they're a bully. Find the derivative of this function. Okay, so this one's a little bit different. We've got trig function. Y prime equals. Take the derivative first of the outer function. What's the derivative of the cosine function? Negative sine. And then we leave the inner function as it is, a to the 5 plus x to the 5, close. And then we have to multiply by the derivative of the inner function, times. Now, what's the derivative of a to the 5? What is a? That's one of the things that's nice about function notation is you know what the independent variable is because it says f of x, therefore x is the independent variable. Here we're seeing y prime of x, which is leading me to believe that x is my independent variable, dy over dx, which means that a is a constant value, an unknown constant value that's being raised to the 5th power. Take a constant value, raise it to the 5th power, what do you get? Another constant. And what's the derivative of a constant? 0. So you could put in a 0 plus if you want, just to really drive home the fact that the derivative of a to the 5 was 0. And then the derivative of x to the 5th is 5x to the 4. Multiplying the 5 out front, keeping the x, subtracting 1 from the 5 to make a new power of 4. Great, after this, the only thing you can do really is clean it up. I would say that it's fairly typical to write this as negative 5x to the 4 times the sine of a to the 5 plus x to the 5. We saw that once previously where we took there was a multiple of like 2x squared or something out here, and we moved it back over and kind of put it into the mix, I said. I think that's how I phrased that. So yeah, that's all we're doing is kind of shuffling things around here. That looks pretty good. This is this is a couple of things. There's a product, and there is an exponential function here. So I'm not so sure that we talked about this explicitly. as pertains to the chain rule, yeah, I don't think so. Well, we'll talk about it during this process. So let's take the derivative of this. Let's come over here, y prime equals, and I'm gonna do something that I don't normally do, is I'm gonna write this as 5 times the derivative with respect to x of x e to the negative kx. I'm really trying to impress upon you that I'm factoring the 5 out of the derivative process. Then we'll take this derivative and then we'll multiply the 5 back in at the end. We'll bring the 5 with us the whole time. We just won't multiply it back in until the end. Okay, so now what? Inside these square brackets, I have a product, so we have to use the product rule. So here's the 5 times, and then I'll put some big parentheses maybe, and I'm going to keep the x, and then I'm going to multiply it by the derivative of e to the negative kx. This is e to an exponent where the exponent isn't just an x. It's a little bit more complex than that. Okay, it's e to the negative kx. So I have to take the derivative of e to the negative kx. And the derivative of that is, let me switch colors, e to the negative kx times the derivative of negative kx, the derivative of the exponent, which is negative k. We'll come back and talk about that in a second. So that was we kept the first factor of x the same. We multiplied by the derivative of the second factor, which was e to the negative kx. And now we're going to add. We'll take the derivative of x, which is a 1, and we'll keep the second factor of e to the negative kx. All right, so let's go back and see what happened here. This factor stayed the same as I started using the product rule. I chose to keep my first factor the same, and then multiply by the derivative of my second factor. Come on. So here's my second factor, e to the negative kx, and the derivative of e to a power. Let me write it even this way. The derivative with respect to x of e to some power like f of x is equal to e to that power, f of x, but then the chain rule says we have to multiply by the derivative of the exponent. When I first learned this, I learned it in terms of u. So it was the derivative of e to the u equaled e to the u times du, the derivative of u. However you write it, we do need to apply the chain rule when we have a number being raised to a more complicated exponent. So that's what's happening here. We've got e to its original exponent, and then we multiplied by the derivative of that exponent. The derivative of negative kx. Now, k is a constant value, and negative is like a multiple of negative 1. So negative 1 times a constant times x. I can factor those constant values out of this little derivative. I can write this as negative k times the derivative of x. Of course, what's the derivative of x? It's 1. So this really says negative k times 1, which is negative k. That negative k. So just in case you were unclear on where that negative k came from, as I was applying the chain rule there, that's where it came from. Can I fit the rest of this? So this is just a matter of cleaning up. Let's get an equal sign in here back to blue. And I'm going to distribute all at the same time. So the 5 is getting multiplied into that first term. Oh, get rid of that. There was a negative sign from the negative k, and then there was a 5, and there's a k, and there's an x, and there's an e to the negative kx. And then the 5 is also distributing out here to the second term, so that is plus 5e to the negative kx. This is an acceptable final answer. Could you factor out a 5e to the negative kx? Sure. I don't know why we do that, but sometimes we do. And if we did, what would we have left? There would be a negative k from the first term, and there's an x in there still, and then you'd have a plus 1 times 5e to the negative kx. That's also an acceptable final answer. Maybe you would see that in a multiple choice option where the bully is terrorizing you and making you do one additional ridiculous step in order to be able to identify the correct multiple choice answer. I don't know. Just don't know. But it's a possibility you could see it show up that way. All right, let's keep moving. So that was a product rule and a chain rule combined into one problem, and part of that process involved the chain rule being applied to an exponential statement, the e to the negative kx. So that was a pretty complex one. This is a product rule with a double chain rule. So I'm going to call this a, and let's a to the 4th and b to the 5. So the product rule says, well, let's keep the first one the same. We'll keep it a to the 4th, and then we'll multiply by the derivative of b to the 5. That's 5 times b to the 4. But then you have to use the chain rule and multiply by the derivative of b, the inner function, b prime. Product rule plus, take the derivative of the first factor this time. The derivative of a to the 4 is 4. Keep the a the same. Decrease the exponent by 1. And then the chain rule. Multiply by the derivative of a. So I'm going to write a prime. And then we multiply by that second factor, b to the 5. I'm going to call that my gift to you to sort of get you started on that problem, get it framed up, and then you go in and take the derivatives and clean it up as best you can. This is, certainly there's a radical here, so the outer function is the square root function. The inner function is 7 plus 2 times e to the 6x. That's an exponential statement, so you've got a little bit of chain rule happening on e to the 6x. So a little bit tricky. Number 7 is a quotient rule. Maybe we'll come back to number 6. I haven't decided yet. Number 7, though, is a quotient rule with a double chain rule on the numerator and on the denominator. Number 8, it's an exponential. Remember I said that the derivative of e to the f of x is e to the f of x times the derivative of the exponent, f prime of x. So this is going to equal, I'll get you started on this one, capital F prime of t equals, we keep e raised to the original exponent. Oh man, this is a bugger. This is, okay, so then we're going to multiply by the derivative of the exponent. Okay, so we need the derivative of the exponent. Equals e to the blah, blah, blah times, all right, now we've got the product rule. Let's factor the 6 out of it. And now we need to keep the t the same and multiply by the derivative dt of the sine of 2t. But check this out. Well, let's finish writing out the product. We can't. Yes, we can. We'll finish writing out the product rule plus we'll take the derivative of t, which is a 1, and we'll multiply by just the sine of 2t. Let me go back here and put this exponent in. When I said it's a bugger, here's why. When you go to take the derivative of the sine of 2t, sine's going to go to cosine, the 2t is going to stay in there, but you have to multiply by the derivative of 2t. So there's another chain rule that we got to hit this thing with. Okay, the first instance of the chain rule was here. We had to multiply it by the derivative of the original exponent on e. And then within the process of taking this derivative, we have to take the derivative of t and the derivative of the sine of 2t. Of course, when we take the derivative of the sine of 2t, there's another instance of the chain rule. We have to multiply by the derivative of the inner function there, the derivative of 2t. So much fun. We're almost there. I'm going to keep making a mess and then I'll leave you to clean it up. Equals e to the blah 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 times 6 times t times the derivative of sine 2t. Derivative of sine is cosine, so I took the derivative of the outer function. The inner function, 2t, that stays the same, but then the chain rule says I have to multiply by the derivative of the inner function, which is a 2, plus 1 times the sine of 2t. You don't have to write that 1 there anymore. I just wrote it to help relate one line to the next. Yeah, you know, distribute that multiplication by 6 and move the 2 over by the t, get rid of the 1. Just clean it up a little bit. Question number 9 is asking for the first derivative and then the second derivative. This is a chain rule problem. The outer function is cosine, the inner function is x squared. Your first derivative is going to, depending on what function it is, mine's cosine, you might get sine, you might get tangent. When you have to take the second derivative in this problem, you're also going to be stuck with a product rule. So be careful, heads up, watch out for that. Number 10 is an equation of a tangent line. I used to have more than one of these questions in this homework assignment. I got rid of maybe all but this one because that process of using y minus y1 equals m times x minus x1, it gets to be kind of irritating after a while. My hope is that you've got it down. Your 0, 1 is your x1, y1 pair. So those are going to get plugged into point slope form as you create the equation for your tangent line. And then you'll need your m value. In order to find m, you're going to need to find the derivative of your y equals equation, and then you'll have to plug in your x1 value, which in this case is a 0. All right, so you'll use the chain rule to find y prime. The 8 will multiply out front. Keep the inner function the same, decrease the exponent by 1, and then don't forget to use the chain rule and multiply by the derivative of that inner function. And then plug in a 0. Oh good, there's more. So this is a product because it's x times the square root. So x is your first function. The square root of 8 minus x squared is your second function. You'll use the product rule. And when you take the derivative of the square root of 8 minus x squared, you'll have to use the chain rule. Don't forget, rewrite this as an exponential equation first. Rewrite this as, well, mine would be f of x equals x times 8 minus x squared to the 1/2 power. And then apply the product rule to that. Here's your product right here. And then you've got some graphing components. It looks like your original function f is in red and the derivative function is in black. So see what you can do about matching those up. Question number 12 is cute. Your original function here, capital F, is equal to f of g of x. If that's the case, then what's capital F prime of x? Just write it out in terms of f's and g's and f primes and g primes, and then use the given information to fill in blanks in order to evaluate f prime of -5. Number 13 is a lesson that you just have to learn on your own. Start taking derivatives. Use the product rule, use the chain rule because you've got e to the -x, so you will have to be taking the derivative of the exponent as part of the product rule and then the chain rule within that, and just keep cranking out derivatives until you get a pattern. If this pattern, so you're going to get f prime of x equals, let's say it's equal to, I'm going to say that it's equal to a. No, I should say it's equal to g of x. And then maybe f double prime is equal to h of x. And then f triple prime, 1, 2, 3, is equal to k of x. And then f quadruple prime is equal to m of x. And let's see, if it's 254, even 6 would be better. Let's say you take 6 derivatives before you see any repetition. Notice that f prime of x that I wrote out is equal to g of x, and also the 6th derivative of the function is equal to g of x. So it repeats every 6. There's a shortcut that you can use. Once you determine how often the pattern repeats, because in my problem I'm supposed to be finding the 500th derivative, I'm going to, do I have room over here? Yeah. I'm going to take 500, and since my pattern repeats, well, let me think. It's, in order to make sure I do this correctly, I always liken it to another problem that's similar to this where there's a pattern. So I to the first power is the square root of -1. I squared is -1. I to the third power is -I. And I to the fourth power is 1. And then it repeats. So there are 4 unique values. So the number of unique values that we're seeing here is actually 5. F prime, F double prime, F triple prime, the 4th derivative and the 5th derivative are all unique. And then the 6th one is the one where I see the repetition. So the first 5 are unique. So I'm looking for the 500th derivative. So I'm going to take 500 and I'm going to divide it by 5. And it goes in 100 times with a remainder of 0. That remainder is the derivative that I want to use. If I had a remainder of 3, I would use the 3rd derivative, which is the 3rd occurrence, 1st, 2nd, 3rd, in my list of unique derivatives. So if this is the 3rd one, and this is the 2nd one, and this is the 1st one, where's the 0th one? It loops back around and would come out to be this one. What's a good analogy to help you remember that? In military time, we can do regular time. If it's 5 o'clock in the morning and you went back in time 5 hours, what time would it be? 0 o'clock? Or would it be 12 again? It would be 12 again. So 0 and the 12 end up having the same position on a clock. So the same thing is happening here. The 0th hour is equivalent to the final hour, which in this case is 5 o'clock, the fifth derivative of our function. So again, a remainder of 0 corresponds to the last position. You're never going to get a remainder of 5. If it was a remainder of 5, you would have divided 5 into the 5. And if we had had a remainder of 4, we'd be here. Remainder of 3, we'd be here. Remainder of 2, remainder of 1, remainder of 0. Full circle again, back to the final hour. You still have to go through and take a bunch of derivatives to see how many derivatives you have to take until it repeats, though. You're welcome. And here's a modeling question. We are 46 minutes in, and there's another modeling question. Let's just see what it involves. A model for the length of daylight in Philadelphia on the 10th day of year is this. Use this model to compare how the number of hours of daylight is increasing on April 21st and May 21st. Okay. On the 10th day of the year. Well, you're going to have to do a little research. You're going to have to figure out April 21st is which day of the year. January, February, March, April. Right, so you're into the 4th month, so you're like more than 90 days in. So this is going to correspond to the like 100 and somethingth day, and this is going to be like the 140 somethingth day. So you're going to need to use those as t values. And then you're going to be plugging those t values into your first derivative. So for April 1st and May 1st, you have different input values, but you're plugging those into the first derivative, which means the first thing you have to do is take the derivative of this lovely equation here, and that is going to require you to use the chain rule. If you want to distribute multiplication by 2 pi over 365, you could certainly do that first. 2 pi over 365 times negative 80 is going to turn into negative 165 pi over 365. Doesn't matter. It's a constant value. Eventually, you're going to take the derivative of it, and it's going to go to 0. I mean, you'll be stuck with it inside the function, but later, when you go to multiply by the derivative of that inner function, it will turn into a 0. So just, use a sharp pencil, use plenty of space on your paper, go slowly, make sure you're applying the chain rule correctly, and don't forget that you have to take the derivative of the sine function first. And then you'll be plugging in t values. What's happening here? The motion of a spring is subject to a frictional force, dampening force, such as a shock absorber, modeled by the product of an exponential function and a sine or cosine function. Find the velocity after t seconds. This is for real. I definitely worked with equations like this in a Calc 3 class, where we were modeling vehicles going around a banked road that had a certain radius of rotation, and these are real-life equations. They're telling you that this is modeling something that involves a frictional force or a dampening force. It's true. Your task here is, this is a position function that you're being given. Your task is to find the velocity function. Position and velocity are related by the first derivative. So take the first derivative of that thing. You're going to be using the product rule and a double chain rule. The chain rule is going to apply when you're taking the derivative of... Oh, come on. Hang in there now. I've got a black screen. Come back. Well, we know what the fix is now. It seems that if we unplug and then plug in again, it should come back to us. Voila. Oh, all right, my timing was a little off. I'll work on that. Double chain rule. You'll need to use the chain rule here when you're taking the derivative of e to this power, and you'll have to use the chain rule when you're taking the derivative of the sine function, because you'll have to multiply by the derivative of that inner function, 2 pi t. And then just clean it up a little bit if possible. It probably won't involve a lot of cleanup. And then you're graphing the position function, which is the s of t function, that original function. And then you're graphing the velocity function. I think here are 2 options and here are another 2 options. And that's it. That's the end of your assignment. You should be pros at product rule. There's like 1 quotient rule problem in there, but noticing when you have to mix in that chain rule. Just take it slow. Make sure that you've got the process down for 1 problem at a time. Show your work on these problems. When you're writing these out, especially if you're one of my students watching this, show your work, put it in a spiral notebook. If you're going through, it'll give you the opportunity to check your work if you get a wrong answer. And if you then go to another piece of paper and you take it from the top and you try it again, you're getting the same wrong answer, you can't figure it out. That's the kind of thing that you can bring to office hours, whether it's my office hours or to tutoring, wherever you're going for assistance with the course. Bring them this work, bring them the original problem, whoever you're asking for help, and have some really nice clear work that you can show them so that they can help you go through and figure out where something went wrong. 1 little missing chain rule can throw the whole thing off. So take it slow, be careful, be patient, and I will see you in the next section. Thanks so much.